I have a new limit here. It is the limit as x goes to 0 of sine of x over x. Now the first thing we try, as always, substitute, simplify. Well, as x goes to 0, substitute sine of 0 is 0. 0 is 0. This goes to 0 divided by 0. So this is the indeterminate form, 0 divided by 0. So that means we need to do some algebra. Well, there's not a lot of algebra we can do. Or do some trigonometry. Well, there's not a lot of trigonometry we can do here. I mean, sine is trigonometry. If it were sine squared or some Pythagoras, but we don't, there's nothing really you can do with sine. So, there's nothing really on offer here. What I'm going to do is I'm going to use the squeezing theorem to find out what this limit is. Now, to do that, I'm going to do a couple things. First, for reasons that will become clear later on, I'm going to draw a picture, and I don't want to use x. And so let's make this statement here. If I have the limit as x goes to, let's say, 2 of some ordinary function like x minus 4. Well, substitute, simplify. That's 2 minus 4 is negative 2. What if I take the limit, what if I change the variable to t? Well, as t goes to 2, this is 2. 2 minus 4 is negative 2. Is it clear it's the same thing? What if I have a different variable? Limit as k goes to 2 of k minus 4. Well, that's still negative 2. Is it clear? The variable we pick does not matter. If the variable you pick doesn't matter, then what we say, there's a phrase we use, it's a dummy variable. It's not inherent in the problem, it's just representing a generic value. And so we are free to choose in this case and in this case as well, we're free to choose whatever letter we like to represent the variable. And because I want to be able to use the letter X in a different context here in just a minute, I'm going to rewrite this. And if you're following along, you might as well. This is T. Now remember, I am not going to expect you. I'm going to show you some work here. Nothing, zero, nothing on this video is something I expect you to be able to reproduce. We are going to get a result at the end. And then in later videos, I'll use that result to find some other things. You need to be able to use that result to find other things later on. But all I'm going to do here is demonstrate the use of the squeezing theorem. You do not need to be able to reproduce that. You do not need to be able to work that. You do not need to be able to do something of that nature. This is not for you to be able to do. This is something I want you to see, understand, and hopefully follow the logic. So, I want to show the limit as t goes to 0 of sine of t over t. I want to find what is that equal to. All right? So, remember the squeezing theorem. The squeezing theorem says we need to have an f of, I'm going to use t. I need to have an f of t less than or equal to g of t less than or equal to h of t. What do I need to have? I need to have g. This is my function whose behavior we don't know. Remember the middle. This is in the metaphor I used before. This is the metaphor of the bucking horse. This is the function whose behavior we don't know and we want to control. So I need to find these two. The one in the middle is the function whose behavior is at interest. This is the function whose behavior is at interest. I want to create sine of t divided by t in the middle of a string of inequalities. Now, to do that, we need to back up a little bit and remind ourselves of some things that hopefully we know already. All right? Now, to do that, I want to do this. I'm going to draw a picture. Suppose I pick a point in the first quadrant. It turns out this argument can also hold for other points. It is a similar argument. We will forego those details. But we'll go through the first instance, and that is to argue this in the first quadrant. Consider an angle in standard position in the first quadrant. Call that angle T. All right? as angle T. And drop a perpendicular, right? And now do this. Complete this circle. All right? Let's assume this is the unit circle. So this is the point 1, 0. Now, one question is, what is the length? All right, let's do this. What is the area of that triangle? Consider the red triangle. The red triangle. Well, I need a new color here. How about some green? Does this green show up okay? See my green? What is that distance? What is that distance? Let's call it, don't know, that's D. Well, we know sine of T is opposite over hypotenuse. So we know sine of T is opposite, which is D, over hypotenuse, which is 1. So this vertical, yeah, of course, if a point lies on the unit circle, the x-coordinate is sine of T. This green distance is sine of T. So now the question is, what is the area of the red triangle? What is the area of this red triangle? Well, the area of that red triangle is 1/2 base times height. 1/2 base times height. So how much is that? 1/2 base times height. Base is 1. What is the height? The height is the green. The height is sine of T. So the area of this red triangle is sine of T over 2. So we have that. All right? Now I'm going to draw a new triangle in here. From this point, erect a perpendicular, extend this line further, and consider this blue triangle. All right? Now the question is, what is that height? Or what is that distance? Let's call this distance D. What is that blue distance D? Well, look, we have a right triangle, right? Here's a right triangle. So from angle in this blue triangle, right, what do we know about T? We know that tangent of T is opposite over adjacent. We don't know how long this hypotenuse is anymore. It's more than 1. But we do know this distance is 1. So we know that the tangent of T is opposite over adjacent. We know tangent of T is opposite, which is the distance we want, divide by 1. It's a unit circle. So this distance D is tangent T. Right? That vertical distance is tangent of T. So, now the question is, what is the area of this big blue triangle? Area of the big blue triangle is 1/2 base times height. 1/2 base times the height. What is the base? The base is 1. What is the height? The height is tangent. So the area of that triangle is tangent of T over 2. So that's the area of the blue triangle. That's the area of the red triangle. And now what I want is the area of this white curved region. This is curved. The curve on the circle going from this point down to here. All right? I want the area of that. So, is it clear that that's called a sector? a sector of a circle is radius, radius, and then the arc. So we have a radius and an arc that bounds what's called a sector. Well, look, the area of the sector is more than the red because the area of the sector includes all this. But the area of the sector is not as big as the blue. So the area of the sector falls in between the red and the blue. Now, from our glory days in basic geometry, we know the area of a sector, or in basic trigonometry. The area of a sector, if we're measuring the angle in radians, and we are, if we're measuring the angle in radians, then the area is 1/2 theta times the radius. The area of a sector is 1/2 theta times the radius. Well, the angle in question is t. The radius, we know, the radius is 1. So the area of the sector is 1/2 times t, or simply t over 2. And so, what do we have? We have the area of the blue is greater than or equal to, it's the big one, the area of the white, t over 2, and that's greater than or equal to the area of the red. All right? And so what I'm doing is I'm gradually creating this. Now the next piece is this. There's a 2 here, 2. I'm going to multiply everything here by 2. I'm going to multiply 2 by all 3 pieces, and so I'm going to clear the fraction. So if you multiply everything by 2, the 2's all cancel out. So we can cancel the 2's. Multiply this by 2, multiply this by 2, multiply this by 2, and those are gone. All right? So now what do we have? I'm going to now multiply through everything that is present, multiply everything that's present by 1 over sine. Multiply everything that's present by 1 over sine. You'll see why here in a minute. Multiply this by 1 over sine. I'm going to forgo the color now. Multiply this by 1 over sine. You'll think, remember the blue is the big one. You'll see why here in a minute. 1 over sine of t times tangent of t t over sine of t. Multiply this by 1 over sine. And now the last piece of the puzzle is I'm going to reform the reciprocal of all 3 fractions. Now, one thing we need to remember from basic algebra, if fraction A is greater than fraction B, if this fraction is bigger than this fraction, when you form the reciprocal, now this is the smaller. When you form the reciprocal, you reverse the direction of the inequality. You can try the various possibilities for that. That's a property of inequality. If this fraction is greater than this is the big fraction, this is the little fraction. When you form the reciprocal, this is now the small fraction, this is the large fraction. So I'm going to form the reciprocal. So this is sine of t over tangent is now less than or equal to sine of t over t is now less than or equal to, I can simplify that on the fly. That's just 1. And the last piece is to simplify this a little bit. I'm going to steal some space by erasing this. What is sine of t over sine of t over cosine of t? Well, you multiply by the reciprocal. Right? Multiply by the reciprocal. The signs cancel. You're left with cosine of t. And so what we inherit from this, I'm going to put it up here in this region here. What we inherit from this and from the triangles, and the sector, we have now established that cosine of t is less than or equal to sine of t over t, which is less than or equal to 1. This is my function f. This is my function g. This is my function h. Small, middle, large. In order to apply the squeezing theorem, I need to know, and I'm interested in what happens as you go to 0. So the question is, what is the limit as t goes to 0 of this function? Substitute, simplify. Cosine of 0 is 1. What's the limit as t goes to 0 of this function? What's the limit of a constant? The limit of a constant is the constant. So what I have now established is g is captured between these two functions. This function goes to 1. This function goes to 1 in the limit. Since this is captured between, we may conclude what we were looking for in the first place. The limit as t goes to 0, sine of t over t is equal to 1. And so, that's the very, very, very long of it. You do not need to be able to reproduce that. You need to be able to take this final result and do things with it. What we have established, what this video really had one point, is to let you see the glory and wonder that is the squeezing theorem. You do not need to be able to reproduce this. You do not need to be able to copy it. You do not need to be able to do something of this nature. What you need to be able to do is assume this now as an established fact. You may now use this to find other things. This is going to be a key element when we get into the next chapter. For now, what we have established is this. We have established the limit is, I'm going to go back to the original variable now. Limit as x goes to 0, sine of x over x is equal to 1. And there's another one similar. The limit as x goes to 0 of 1 minus cosine of x over x is equal to 0. This, you can use this to prove this. That's a possibility. Or you can multiply by the conjugate. Once you've established this, it's not very challenging to establish this. We could go through a similar argument, or you could use a trigonometric identity. But for our purposes going forward, we may now use these two limits as established facts. You may now use this to find other things. You may now use this to find other things. There are two key elements that we're going to be using next chapter when we work with derivatives. Not only may you use these to find other values, I will expect you to use these two to find other values. More on that in coming lessons.